By the mid-1400s, Portugal was essentially being strangled by a monopoly. Every shipment of spice from Asia had to pass through Ottoman-controlled trade routes before it ever reached Lisbon. The markups were unsustainable, but they had no overland route to contest the situation. Their only option was the Atlantic, an environment no European ship had mastered well enough to go south and reliably return. They needed a specific tool for a specific mission. This is the engineering behind the caravel and the technical cost of breaking that monopoly. To understand why the caravel had to exist, you have to look at what the Portuguese were currently trying to sail: the European cog. Cogs were heavy, boxy cargo carriers, built for the Baltic and North Sea timber trades. They relied on a single, massive, square-rigged sail. Square sails are exceptional when the wind is directly behind you, pushing thousands of pounds of timber or grain across flat water. However, the Atlantic doesn't offer a permanent tailwind. Once you sail south past Cape Bojador off the coast of Western Sahara, the prevailing trade winds blow relentlessly from the northeast. A square-rigged cog could easily run south with the wind at its back, but turning around to get home meant sailing directly into that prevailing headwind. A square sail simply cannot create aerodynamic lift. It acts purely as a parachute. A cog caught in those trade winds was effectively trapped in a one-way corridor. To solve the headwind problem, Portuguese shipwrights in the yards of Lisbon and Sagres abandoned traditional Northern European ship design and combined two distinct regional technologies. First, they replaced the square rig with the lateen sail, a triangular rig borrowed from Mediterranean feluccas and Islamic dhows. Suspended from a long, angled yard arm, the lateen sail worked less like a parachute and more like a modern vertical airplane wing. By adjusting the angle of the yard against the wind, the sail generated a low-pressure zone on its leeward side, producing aerodynamic lift that pulled the vessel forward even when heading close into the wind. Second, they overhauled the hull construction. Traditional cogs used clinker planking, where heavy oak boards overlapped each other. Clinker hulls were strong, but the overlapping ridges created tremendous hydrodynamic drag in open ocean swells. Shipwrights switched to carvel planking, laying smooth oak boards edge to edge over a strong internal frame, flush-caulked with oakum and pitch. This reduced water resistance significantly and yielded a lighter, much more responsive hull. The result of this hybrid engineering was the caravel, and later the caravel redonda, with a displacement usually between 50 to 100 tons, a shallow draft, and a length-to-beam ratio of about 3:1. The vessel was fast and exceptionally maneuverable. More importantly, it unlocked the physics of tacking. By angling its lateen sails roughly 45 degrees relative to the bow, the crew could sail zigzag patterns across the wind vector, a maneuver known as tacking. For every 2 miles sailed diagonally into the wind, the ship gained ground northward. Coupled with a lateen-rigged stern sail acting like a hydrodynamic rudder, small crews of 15 to 25 sailors could rapidly trim the yards and shift course, without the massive physical labor required on heavy square-rigged vessels. This mechanical agility changed maritime tactics entirely. In 1434, Gil Eanes used these early hull and sail refinements to finally pass Cape Bojador, a geographical barrier that had terrified European mariners for centuries due to shallow reefs and violent coastal currents. Instead of fighting the coastal currents head-on, Portuguese captains developed the Volta do Mar, literally the turn of the sea. They sailed hundreds of miles out into the open, deep Atlantic, steering away from their destination to catch the broader oceanic gyres that would carry them around the adverse headwinds and back home to Portugal. It was a strategy that required absolute trust in the ship's ability to handle high seas swells and sail close to the wind in open water. The engineering payoff was immediate and lucrative. By bypassing the Ottoman land routes and Venetian middlemen, a single caravel returning to Lisbon, loaded with African gold, ivory, and grains of paradise, could cover the entire cost of its construction and expedition in a single voyage. Because the caravel required a fraction of the crew of a traditional galley or larger merchant vessel, operational overhead was incredibly low. It was the ideal long-range reconnaissance craft, cheap to build, cheap to sail, and capable of returning from places no European vessel had ever navigated before. The caravel was never meant to be a heavy merchant ship or a warship. It was a highly specialized mobile laboratory, engineered to solve a specific hydrodynamic and aerodynamic problem. Eventually, As trade routes expanded around the Cape of Good Hope into the Indian Ocean, the caravel gave way to larger, multi-masted carracks and galleons that combined the caravel's lateen tacking agility with the massive cargo capacity of square rigs. However, without the caravel solving the fundamental physics of headwind navigation, the global maritime era simply couldn't have begun. It was the crucial technical bridge that unlocked the oceans.